ask the question on the application of remote sensing. So today we will be moving, but before that, try to find out what is the space vision India 2025. That means when we are talking about the remote sensing or satellite technology, we must know how do we see where are we heading in India. So at the national level, friends, look at what is the vision for India. So what we find that we are looking for satellite-based communication and navigation systems for rural connectivity, security needs, and mobile services. This is a very important task before us to improve the communication and navigation systems. Now, when I'm talking about communication, I'm talking about one set of satellite. When I'm talking about navigation, I'm talking about a very different set of satellites, which we will be discussing maybe in the subsequent days. Number two, we want to have an enhanced imaging capability for natural resource management, weather and climate change studies. Again, this is a very important vision for the nation that we are looking for very high quality images, which can provide us a lot of information about the different aspects of nature, and we can use them for different purposes. At the same time, we are looking forward for satellites which can give us the best quality weather forecast, which can be useful for climate change studies, etc. This is another vision which any student or a scientist can use it for their upliftment. Third vision relates to the space science missions for better understanding of the solar system and universe. Now, when I say so, one point should be very clear to all the participants today that, friends, we know very little. That means the unknown is still bigger than the known, which means there is a lot of scope to know more and more about the solar system. We are knowing very little, and therefore the space technology matters a lot. So we are looking forward again for planetary explorations. We are looking forward for reaching the different planets and to understand their surface, to understand their environment. There is a lot of work going on in different parts of the country. This is another vision. We have to further expand it. We are looking for development of heavy lift launchers. Friends, it is very important for all of you to understand that, see, as far as satellites are concerned, see, there are two parts. One is satellite itself. Another is a launcher which takes the satellite from the Earth and puts it in the Earth's orbit or in the space. And that is how we put them in two categories. One is called as the PSLV. PSLV stands for Polar Satellite Launch Vehicle. And then we have GSLV, that is Geostationary Launch Vehicle. So what we find that we have two different kinds of vehicles which carry our satellites and they are put in the space. So one is for the satellites which are put in the polar orbit, another is which is put in the geostationary orbit. Here we want to introduce much stronger the vehicles so that we can lift the very heavy satellites also. Next, reusable launch vehicles. So if we are using a launch vehicle, remember when the vehicle goes up with the satellite, normally this becomes useless. But then we have to bring back those vehicles so that we can reuse them. And this is another important development, and this is another important area in which our technocrats and in which our technical experts can look forward for the future. Then this is another important area where we are looking forward, that is human space flight. Though a few Indians have already gone in space, but they have not gone in our own indigenous satellites. They have gone either in the satellites of the US or with the satellites of the Russia. So what we find that we are looking forward that we can put our own people in these space flights and they can go and explore new avenues. Now, this is the vision with which our scientists have to work as far as the satellite technology is concerned. Now, look at it. Now, I'll focus on remote sensing part of it. So, what we find that by now, what has happened? So yesterday you learned about the basics, elementary of the remote sensing. So what has happened? Remote sensing has enabled what? Mapping. Remote sensing has enabled mapping. It has enabled studying. It has enabled us monitoring and management of various resources like agriculture, forestry, geology, water, ocean, and name any. We are there is some disturbance coming out.
Hello.
Kindly mute. There is some voice coming out of a child. Is it okay? Okay, fine. So what you find that remote sensing is a tool for you in which Monica.
Yes, sir, I'm doing. Madhu, ma'am, please. Account पर रखा है. कृपया लाइन पर बने रहिए.
Is it okay?
Yes, sir.
Can I move further? Okay.
Yes.
Kindly give an instruction to everybody that they should switch off their mobiles. At the same time, they can mute themselves so that we can continue our discussions and we are not disturbed. So friends, yesterday itself it was very clear that remote sensing is a technology for us which is going to be used for gathering of information. We want to gather data. We want to generate a lot of data. And this data, so this is a data gathering tool. I again repeat, so remote sensing is going to provide a huge amount of data which can be used depending on our objective. So this is an excellent tool before us. It has further enabled monitoring of environment and thereby helping in conservation. So this is also used. In the last 5 decades, it has grown as a major tool for collecting information on almost every aspect on the Earth. With the availability of very high spatial resolution satellites in the recent years, the applications have multiplied. So what we find that when the technology improves and we keep on improving it, we find that the applications also multiply. In India, remote sensing has been used for various applications during the last 5 decades and has contributed significantly towards development. So what we find that the purpose of the remote sensing is already there. As far as the application is concerned, because yesterday you were asking about it, friends, remember that application of any technology depends on, number one, the objectives of the study. And when I say here, it is very, very important for you that objectives could be very useful. So you can use the technology. You can even misuse the technology. And you can also abuse the technology. I again repeat. So if you have the technology can be used. And as an academician, I'll support only the use of technology. But then remember that many people misuse it and many people abuse it also. That is not the purpose of any academic work. So if you want to use the remote sensing, so the objective should be clear. Why do you want to use remote sensing? You are going to use remote sensing because you do not have access for some data. You do not have access because of what? You don't have access for the data because the data for an area which you want to acquire, the area is far away from you. The difficulty in reaching there is there. There is no road connectivity. There is no possibility of reaching the place. So, but you want the data. You want the data. So how will you get the data? So earlier we used to walk for months together with so many instruments on our back, and we used to collect some data of some places for some time, but then it was never complete data, friends. So it was very important that without facing all those difficulties of traveling from place A to traveling to a most difficult place, we developed a technology that we can get the information either by flying in the air, getting the area recorded on the photographs, or we can now run these satellites over an area and we can get the images, and then when the images are before us or when the photographs are before us, now look at the advantages when we have them. Now, if you have a photograph of a place, now you can look at this photograph layerly in your lab as many times as possible. Whenever you want to see that, you can see that. So what you find that you have a lot of freedom of seeing the area without facing the difficulties of hot weather, cold weather, stormy weather, rainy weather, no issue. You are watching that area, so you are not only watching but you are observing the area very minutely, and you can get the required data of that area. Now here it should be very clear that what you want to see. If you want to see a particular thing, then you have to be focused on that only. But then remember that in our day-to-day life, we watch things, but we don't observe things. As a scientist, you have to learn to observe things, where you observe a particular phenomenon or a process of the nature very carefully. So remember here that objectives are always dependent on the aim which you have in your mind, right? So if the objectives are clear, you can apply this. Let me give you an example here, friends, so that things are very clear. We had recently invited some students for identifying the applications. Normally what happens that when we talk to them, they say they have a complaint. The complaint is that, sir, we are not getting the data. Now I asked them, what kind of data you want? Sir, we are not getting the latest data. I said, okay. So then we asked them, what is your objective of doing? So, and then they said the quality of data is also not good. So two things were there. Number one, they were of the opinion that they want the latest data. Now remember here, friend, that among all the tools available right now on the earth, remote sensing is one of the tools which can provide you the near real-time information. I again tell you, the remote sensing is the only tool available with you which can provide you the near real time more data. That means what has happened today in the morning can be seen by you anywhere in the world if you are using the remote sensing technology. Earlier, we were dependent on the maps. So what you find, the maps are basically the compilation of information collected over a period of time, and then they are symbolically represented on a piece of paper. Now that information which is displayed on the map is an old information, whereas you are looking for the new information, and for the new information you have to depend more on technology. So if you want to understand what was happening in the Galwan Valley yesterday, then you have to depend on the satellite images which have taken the images of that area. And then if you want to understand what was happening in the last 5 days, that means you have to focus the images of 5 different days. Here again, you have to keep in mind that am I able to get the images of every hour? And then you'll find that to get the image of every hour is not possible of the Galwan Valley. Therefore, you have to further realize that how to get more and more information. And then maybe which satellite is giving you the information? Is it your own Indian satellite, or is it the satellite of United States, or is it the satellite of some other nation? That means you have to be very clear in your objective that yes, there are satellites which can give me the information and we own it. We have satellites, but we don't own them, so we have to purchase the data. We have satellite images which are in public domain, they can give you the information. What kind of information? What quality of information? So any researcher, any student, any teacher, any scientist who wants to use the remote sensing, he or she should be very clear. So what happens, friends, that suppose you are interested to study the forest distribution, right? Now to study the forest distribution in India, suppose. So do you really need the data of every hour? No, not at all. Do you need the data of every second day? No, not at all. Every week? No, because here comes the very important that the processes which operate in the nature, there are range of their activities. Some of the things on the earth in your life, they change every minute. Some of the things they change every day. Some of the things change every week. Some of the things change every month. Some things change every quarterly. Some things change every half yearly. Some things change once in a year. Some things change after decades. And therefore, what you find that the need of data will depend on what kind of study you want to do. So suppose you want to study the forest, we do not require the satellite images of every hour. We do not require it for every week because we know that forest will not change. So maybe you can look for information, maybe the satellite images of two different seasons. So what happened in the one part of the season and what happens in the post-monsoon season. That could be a kind of study. So you don't require a large number of satellite images. You require only 2 time period data, and then you can compare it. I hope the objective should be very clear when you make a study. Number one. Number two, the scale of study. When I say scale of study, it is very important, friends, that whether you want to go for the micro scale study or whether you want to go for a macro scale study or whether you want to go for a meso scale study. Now, somebody who wants to make the study of a continent or of a country or of a small district or of a village, depending on his or her requirement, the data can be searched, and therefore it is very, very important. Having said so, friends, it is very important that see you cannot completely believe that if you have the remote sensing data, you can do wonders. No. Remember that remote sensing data can be best understood only if you have a background in some important fields. For example, you must have some understanding about the cartography. You must have some understanding about the use of computers. You must have some understanding about the softwares which help you in image analysis. You must be having some idea about the use of GIS because ultimately remote sensing is data. It is going to give you the data, and this data is to be integrated in the kind of work you are looking for. And therefore the training in identifying the features or understanding the photographs or satellite images or photogrammetry is very, very important. The application of the image analysis softwares is very, very important. The integration of information of remote sensing in the GIS domain is very, very important, and therefore all your application will depend on these things. Very, very important. Now, since yesterday I told you about the satellites, remember, friends, satellite launch is one part of it, satellite is another part of it. The satellite gives you the images, or the aerial photographs give you the photographs. Now, when you look at the photographs, there are 4 different kinds of resolution, which is very important for any remote sensing scientist. And what are these 4 types of resolution? Number 1, the spatial resolution. Number 2, the spectral resolution. Number 3, the temporal resolution. And number 4, radiometric resolution. We will be trying to understand each one of them slowly so that it goes in your head and then things are very clear to you. Let us focus on what is spatial resolution. Spatial resolution dictates the amount of discernible details in an image, the size of the smallest possible feature that can be detected. So what you find in general, the spatial resolution depends on the instantaneous field of view, also called as IFOV, of the implemented sensor. The IFOV is the angular cone of visibility of the sensor. The projection of the IFOV into the surface of the earth is known as resolution cell. The spatial resolution is mainly controlled by the separation between the sensor and the target. Now, in simple words, if I have to explain it, Look at it very carefully, friends. Friends, suppose you come to know about a launch of a satellite, and the news reader is reading that this particular satellite will have a spatial resolution of suppose 15 meters. So for a layman, what does it mean? Now, the moment you come to know that this particular satellite has a spatial resolution of 15 meter, in simple words, it means that this particular satellite image will be able to help you in detecting the objects which have a dimension of at least 15 meter by 15 meter. That means object smaller than this cannot be detected on the image. I again repeat. So if a satellite has a spatial resolution of 15 meter, remember that you cannot detect the objects having a dimension of less than 15 meter by 15 meter. Now let me move further and help you in understanding. Then suppose you want to detect the objects of smaller size. That means you have to improve the spatial resolution of this image. Okay, that means you have to equip the satellite with better technology, and then you find that if you want, then you get a spatial resolution of 5 meter. That is what the meaning of it. Its simple meaning is that now you have an image on which you can identify objects which have a dimension of 5 meter by 5 meter. So now we have two examples. In the first example, I told you about the spatial resolution of 15 meter. In the second, I said 5 meter. Which one is better? Obviously, spatial resolution of 5 meter is much better than the spatial resolution of 15 meter. Now we can improve it further, and we can think of 1 meter. Then let me tell you that USA has a technology in which they can see the objects of the dimension of your nail size. So they can identify the objects on the earth having the size of 2 centimeter by 2 centimeter. And therefore, you can understand how advanced they are. In India also, in the non-public domain, we are in a position to detect objects of 0.5 meter by 0.5 meter. That means we have also improved. Remember, friends, starting from 1972, when the Landsat was launched, till now, a lot of changes have taken place, a lot of improvement have taken place. In the initial years, the spatial resolution of satellites was 70 meter by 70 meter. Now we have come to the nail size 2 centimeter by 2 centimeter, and that speaks about the kind of improvement which has taken place in the field of remote sensing. So I believe that all the participants have a clear vision about the concept of spatial resolution. I move further. So you can see that how the spatial resolution of satellites are there. So in the first image, you can see that 1 kilometer is the spatial resolution. In the second one, we have 23 meter. In the third, we have 360 meter, 5.8 meter, 188 meter, and then 1 meter. So what you find that in the first image and the sixth image, the kind of features which you can find, they are much better in the sixth image as compared to in the first image. But then the first image had a different purpose, and the sixth image had a different purpose. If we want to have a mere reconnaissance of the country, then even 1 kilometer by 1 kilometer of spatial resolution is equally good. And if you want to identify the buildings or even the road pattern in a particular city, then the 1 kilometer will not be useful. We go for the 1 meter and maybe more than this. So I have given you the complete understanding about this. Second is called as spectral resolution. What is this? So yesterday, very thoroughly, I talked about the use of electromagnetic spectrum for the remote sensing. So look at it. So what you find that this talks about the visible band of it. Now the visible band has a range of 0.4 micrometer to 0.7 micrometer. This is the wavelength. So in that wavelength, we can further subdivide it, maybe 0.4 to 0.5 as one band, 0.5 to 0.6 as another band, 0.6 to 0.7 as third band, 0.7 to 0.8 as the next band. So what you find that we can split, and when we split the bands, the ability of getting information more and more is possible. What does it mean? It means that in different bands, different objects will be reflecting differently. I again repeat, in different bands, different objects will reflect differently. And this is a very simple technology, because you must have seen in the movies also that how the interplay of the light changes the entire understanding. Okay, here also what we find that when we split and when we try to see a particular thing in a particular band, the visibility of that particular object is very clear. Here, I would like to make things more simple, friends. What have you done? Have you seen the heartbeat of a patient on the screen? Can we see the heartbeat otherwise without opening the heart and making it on the screen? No. But what you see, you see the graphic presentation of the heartbeat or the pulse rates. Now, what is that? What is that? Friends, the technology converts that information so that the information becomes visible to you. So similarly, what you find, can we see the X-ray with our naked eye? We cannot see the X-ray with our naked eye, but we make them see. We try to see them on the screen, and then we can see that this is the X-ray. Similarly, what you find that infrareds can't be seen, but then we try to show them by having a false color. So we add a color so that even the infrared can be seen. So what you find that even that those things which are not visible to us, they are made visible with the help of technology. So we have to understand about so what is this spectral resolution? Spectral resolution describes the ability of a sensor to define fine wavelength intervals. That's what I was talking about, the bands 0.4 micrometer to 0.5 micrometer, 0.5 micrometer to 0.6 micrometer, and so on and so forth. This is all about the visual band. We can put them together also, and then we can have the visual band and so-called the photographic spectrum. So for the photographic spectrum, we use the visual band plus the near infrared as well as the near ultraviolet, and both put them together, the photographic spectrum becomes larger as compared to the visual band. The visual band is 0.4 to 0.7, whereas photographic spectrum ranges from 0.3 to 0.9, and that becomes much bigger. So the finer the spectral resolution, that means if it is very fine, the narrower the wavelength range of a particular channel or band. Black and white films record wavelengths extending over much or all of the visible spectrum of the electromagnetic spectrum. Color film is individually sensitive to the reflected energy at the blue, green, and red wavelengths of the spectrum. Color film has higher spectral resolution when compared to black and white film. Here it is very important, friend. You must have learned in your school days about the so-called Vibgyor. Now the Vibgyor is nothing, but then see, it is the visible band of the electromagnetic spectrum. So what we do, in order to understand things, we try to find out each wave band with a color. And therefore what you find when you say Vibgyor, the R comes in the end, V comes in the beginning. So if R comes in the end, it means it is a long wave range. And when it comes to the violet is a short wavelength. Okay, so what you find that between the and our eyes are more sensitive to long wavelength. Therefore, we use the red color for the traffic lights. Okay, and that is how the whole science is going to help us in our day-to-day life. So, in the same way, when we are combining all the colors put together, we call them as visible light, and then we use them for the different purposes. So it is very important that what kind of spectral resolution is there. So if we have we are trying to get the images in band 1, band 2, band 3, or we are trying to get the images whether it is in all the bands put together, or we may split these bands further, all mechanically, and that is very, very important, friends. The third part is called as temporal resolution. Friends, I told you today in the beginning that depending on our objectives, we need the data. whether I need the data for every day, whether I need the data for every week, whether I need the data for every fortnight, whether I need the data for every month or year or decade, it will be deciding. But remember that when we are talking about the satellites, now here it is very important for you to understand how the satellites actually operate. And I will be showing you one video and I'll come back to the presentation again. And let us first have a video to understand. Watch this carefully. This is a video about a satellite. Is my screen visible to everybody? Monica, my screen is visible?
Yes, yes, sir, it's visible.
Okay. So, friends, what you are seeing on the screen is there is a satellite, and this satellite is moving around Earth. But while it is moving, you can see a thread-like string. Okay, remember that it is just an animation. There is no thread as such. Okay, but then what is the purpose of showing you here that this satellite is looking at a particular part of the earth constantly. While earth is moving, the satellite is also moving, so both of them are moving, but while they are moving, the satellites keep on looking at a particular part of the earth. Such satellites are called as geostationary satellites, and we use them for the purpose of satellite telecommunication. We use them again for satellite communication purposes, and we call them as geostationary satellites. Let's look at further. Now this was one kind of satellite. Now we are going to put the other satellite. Okay, and this is called as polar sun synchronous. Or watch it carefully. So you must have seen that this particular satellite is crossing over pole. It is not fixed to a particular point of the earth, rather it is moving from pole to pole. Look at the circle. So it is going from pole to pole. So it is called as polar sun synchronous. Look at it further. Thank you. So let's move further. So friends, it is very important to understand the whole concept. So what you find that in case of the polar sun synchronous satellites, remember they are used for the purpose of remote sensing. Here I'll again repeat that the remote sensing satellites are polar sun synchronous and they are placed at an altitude of about 600 kilometers from the Earth's surface. Whereas the first satellite, which was the geostationary in nature, which is used for the purpose of communication or television, they are placed at a height of 36,000 kilometers. Remember here, why can't we use a satellite which is in geostationary mode for the purpose of remote sensing? Because they are far away from us, and if you use any sensor or scanner right on today, then you'll find that the quality of images will be very, very poor. Right? Therefore, we don't use them. So what we do, we have placed the remote sensing satellites at a lower altitude. From there, we can get the better image of the Earth. This is clear. Now, if you have observed the video very carefully, you must have realized that while Earth was moving, the satellite was also moving. But Earth was moving from west to east direction, whereas satellite was moving from north to south every time. That means this satellite is never pointing a particular part of the Earth. Every time in front of the satellite, a new space comes. Now, suppose you are in Hyderabad. Now, can you think of that this remote sensing satellite is always looking to your area? Not at all. Or suppose you are in Delhi, can you think of that this satellite will always look at Delhi? Not at all. So this satellite will pass over Delhi only once. Okay? Now, by the time it comes for the next round, Delhi has shifted to other area and maybe in front of it, the Karachi is there. Maybe the third day, it is not there, but the Cairo is there before it. Next day, it is not there, but it is the Atlantic Ocean over it. And next day, it is not this, but the New York is below it. And therefore, what you find that every time, this satellite will have a different place below it. But then if you want to get the image of Delhi, then you have to wait for, depending on the speed of this particular satellite, and suppose it is, you are told that you can get the repeat of this image after 18 days. That means the temporal resolution of this particular satellite with respect to Delhi is 15 days. That means after every 15th day only, you will be getting the image of Delhi similar to what you got 15 days back. So you can compare Delhi, which was there 15 days back, and you can compare Delhi, which is 15 days today. Next image will come to you after again 15 days, and so on and so forth. So what you find that different satellites over the years have different temporal resolution. So some satellites which have a resolution of 11 days or 12 days or 15 days and 30 days, which one is better? Now a gap of 30 days is a long gap. We want to improve it further by increasing the speed of our satellites, and we are trying to reduce it. So we are trying to reduce from 9 days to 8 days to 7 days and so on and so forth. But if you want more and more information every day, remember here, can you depend on one satellite? No. In that case, we have to take the use of band satellites. So suppose we have 5 satellites. So one satellite passes over Delhi on day 1. The second satellite passes over Delhi the day 2. The third satellite passes over Delhi on day 3. So if you want such information, then you cannot depend on one satellite. Rather, you need multiple number of satellites so that you are getting images not from the same satellite, but from different satellites. And that is a very, very cost intensive exercise. So what happens? Then we take help of the satellites which have been launched by USA or by Russia or by France or by Germany or even China and so on and so forth. So what we require? We require an inter-country coordination for data sharing. So whenever we need data and whenever they need data, we share with each other by paying money or by even by courtesy also, depending on the situation. This is very, very important. So friends, remember here that if Earth is an oblate spheroid, and if the satellite is passing over the pole again and again, then the temporal resolution of the polar areas will be small or high, because for the polar areas you can get the image every day, because the satellite has to pass from the pole again, pass from the pole again, the next. So in every orbit the satellite will be passing over the poles. That means for the polar areas, image of every day is available. But for the equatorial area or for the tropics in which we are located, we cannot get, because the surface is too big. So maybe on the first day, satellite is passing through Assam. The second day, it is passing over the Banaras, and the third day it is passing over Delhi. Fourth day it is passing over Jaipur, and therefore, what we find that this is going to change. And this is very, very important, friends, to understand. Look at this. Look at this image very carefully. So what you find that when the satellite is moving, it is not complete circle formation. So in the first image, you can see that it was over India, but then by the time it comes, the India has shifted, and in the when the satellite comes, it is very close to Africa. In the second one, what you find that in the third orbit, it is on the middle of Africa, and in the fourth orbit, what you find that it has crossed the Africa also. That means we do not have a technology in which we can get the image of a particular part of the Earth regularly every day using one single satellite. No, it's not possible as on date. This is called as temporal resolution. Very, very important. So does it mean to us? Temporal resolution of remote sensing system refers to the frequency with which it images the same area. Frequent imaging is important for disaster and environmental management. For example, floods, oil leaks, spread of forest disease from one year to the next, change detection applications. So depending on the nature of work, suppose you are looking for a work in which everyday change is very important, then you have to use many satellites and the data. But if you are using the study in which the yearly change is there, then you don't require a high temporal resolution data. The fourth, okay, is it okay? So the fourth is called as radiometric resolution. Now, what is this? So, what you find that we were talking about the electromagnetic spectrum. Here, what you find that we have to define the categories in which the whole data can be divided. So if we are using 6-bit, that means the whole data can be classified into 64 subtypes. If you are using 8-bit types, that means the whole data can be split into as many as 256 subdivisions. And depending on it, so if more and more minute divisions means more and more precise data. So what you find, depending on what kind of radiometric resolution we have introduced in the system. So what you find that if it is 10-bit range, then we can have a sub-classification of 1024 subcategories, and this is going to help you in much better classification of the whole data. And therefore, what does it mean to us? It means radiometric resolution of an imaging system describes its ability to discriminate very slight differences in the recorded energy. That means if you want to discriminate between A object and the B object, you require a high radiometric resolution. The finer the radiometric resolution of a sensor, the more sensitive it is to detect small differences in reflected or emitted energy. For digital imagery, the radiometric resolution is defined by the number of bits used for coding the recorded gray values. By comparing a 2-bit image with an 8-bit image, one can see that there is a large difference in the level of discernible details. So what we have learned? We learned about 4 different types of resolution. First, spatial resolution, right? Then we learned about the temporal resolution. We learned about the radiometric resolution, and therefore all the 4 the resolutions are very important. Here It is very important, though I hope you all know about it. This is called electromagnetic radiation, and we have the simple method of explaining what is wavelength and how the short waves and how the long waves are explained. Here, look at this spectrum. What you find that the visible band is very, very narrow. Since the visible band is very, very narrow, we are trying to use different parts of this visible, the total electromagnetic spectrum for the different purposes. And depending on it, we can collect the data, and this is to be scientifically done. So what we find that the signatures of different objects in different wave bands will be different. So what you find that if you look at this very carefully, so what you find that this is the signature. That means more and more reflectance comes from the soil in the wave band between. Look at it; it has gone to 1.5 to 2. Okay, and so in this band it reflects more. Okay, whereas if you look at the other part of it, water, for example, water has a very high reflectance value here, right? But then it goes down when we increase the wave bands. So different kinds of objects have different level of reflectance. Let me again simply explain you that when you are using the energy, every object will not have similar reflectance. In simple words, suppose you are throwing a ray of light on a snow or on ice. Now, from ice, the reflectance will be very high. If you are throwing the same light on a tree which is green, then you'll find that the reflectance is very, very low because the tree is going to absorb it. Or if you are going to use the same light on water which is turbid, then the reflectance level will be different. And if you are using it in the clear and clean water, the amount of reflectance will be very different. So normally the scientific community tries to understand the objects with the help of the kind of reflectance. In simple words, if you observe the nature, you will find that those objects which absorb more and more energy, they look you darker. Those objects which reflect more and more light, they appear you as lighter, and they appear brighter. Okay, and that is very, very true. So even in your human body itself, you'll find that your hairs, though I don't have, your hairs are going to absorb more light, therefore they appear dark, and your face absorbs less light, so we have more reflectance from our face. So this is to be understood in scientific terms. So when you are using the visible light or any energy, remember that we basically capture the reflected part of it, and this reflected energy is going to help us in understanding the kind of objects which is before us. Friends, having learned the basics, in order to interpret the images, it is very important that we must focus on different kinds of elements. So whenever there is a photograph before you, remember friends, when you have a photograph before you, if it is a black and white photograph, there is no object. You can't touch the object. You can't see them in 3 dimensions. What is there? That particular photograph, which is black and white, is merely the shades of black and white. Just nothing. So there are different types of shades which are there on that page, and then with the help of that, so what you look at it? As a scientist, you have to interpret that image with the help of the shape which emerges from that image. So shape is very important. So many natural and human-made features have unique shapes. In your life, if you ask the question to yourself, which particular body, man or nature, will have more geometric shapes? Answer is very simple. Man is going to create more geometric shapes. So our buildings are geometric shapes. All our cycles, all our tires, everything has a circular dimension. In the nature, friends, you'll find that very, very small things are in the form of geometric shapes. Look at your own body. If you have to define your own body, you cannot define your own body in any strict geometric shape. It is neither triangle, nor circular, nor this oblate spheroid, you cannot put them in any form because your fingers, your hairs, your ears, your nose, everything is natural, and then their shapes cannot be strictly put in any geometric form. So if you have to simply identify on a photograph which one is man-made feature, which one is the natural features. Merely looking at the shape, you can identify. For example, look at this. Look at this very carefully, friends. So what you find that this aeroplane has a shape, and you can identify it because you know the shape. The shape is already there in your brain, so you call it a shape. You're not calling it apple because you know that apple is not like this. The shape is giving you the identity that this particular thing is a plane. Look at the other part of it. So what you find that we have a pentagon. So the pentagon is there. So you know about the pentagon, and the shapes are going to help you. Look at this natural flowers. And then you say that they appear different. So the first image of a plane and the last image of the flowers, they are very, very different. Very, very different. So this is man-made, this is natural, because their shapes can't be put together. So when you are looking at the images, friends, shape is very important. Second point, shadow is equally important. Shadow is equally important. So look at this image very carefully. So what you find that we have a building here. So you can see the building, and this building is casting shadow. The moment on the photograph you find shadow, remember that the shadow is cast only by the objects which are vertical. That means this is not a flat plane surface because it is casting. Look at this. This building is casting such a shadow. This particular road is casting shadow, and therefore you can see that shadow. This particular tank is casting shadow. That means they are vertical features. That means while you are interpreting the image, shadow is equally important, friends. I'll give you an example here. That on one particular satellite, there were two images which were looking alike. Both of them were white in color. And it was difficult for us to identify whether it is a snow or whether it is cloud. So how to identify it? So the only method which was there before us was that since cloud is in the sky, okay, in the presence of light, the cloud will cast shadow on the ground. And if it is snow, if it is the ice is on the ground, so it is not going to cast a shadow. So one can easily differentiate between the cloud and snow-clad area, because if it is cloud, though both of them appear the same in color, so cloud is in the air and cloud is going to cast shadow. So, and as scientists can tell that this is not the snow, but this is cloud which is visible. Else, if an untrained person is there, the untrained person will say that this is a snow-clad area. No, it's not snow-clad area. It is the cloud in the air, because the cloud is casting its shadow on the ground, and from the shadow, one identifies that it is different from the snow. So shadow plays a very important. Tone and color. Look at this. So the tone and color also helps you to identify. So what you find that this image is different from this image, and the tone is there. And then it is very important that if you have to understand the tone, a band of EMR recorded by a remote sensing instrument can be displayed on an image in the shades of gray ranging from black to white. These shades are called tones. So the shades are called tones and can be qualitatively referred to as dark, light, or intermediate. So you can see this. The different shades are there. Look at these shades, look at these shades, and so on. So this is very important. The texture is very important. That means repetition of the same feature. So look at this. Look at this, how the texture is there. So you must have used the word texture, fine texture, coarse texture. Fine texture means when the spacing between one object and the other object is too little. So the texture also helps you in identifying the features. The pattern also helps you. So look at the pattern. So you can say that this is a pattern formed by the objects, and the pattern helps to identify whether this is a linear pattern or whether these are the planes available, these are the natural patterns available. Height and depth is equally important. So look at this. One can easily identify whether it is depth or whether it is height. Associations are also important. So you can identify that if it is a coastal area, what will you find? You will find the boats, you'll find the steamers. But if it is Delhi, you'll not find the boats and steamers in Delhi because it is a different location. So you can easily relate that if it is a power plant, near the power plant, what kind of things will be there. So near the power plants, things are very different. You are not having the universities near a power plant. So you have to identify, because you are associating that what could be there, and then you associate. So friends, let us look at some applications, which again I repeat, the application will always depend on what? It will depend on your objective. So one can study the groundwater prospects and recharge zone mapping. You can think of national wasteland monitoring. You can think of national wetlands inventory and assessment. You can think of snow and glacier studies, coastal zone studies. You can think of forecasting agricultural output using space agrometeorology. You can think of assessment of irrigation potentials and accelerated irrigation benefit programs. You can also think of national agricultural drought assessment and monitoring systems, biodiversity characterization, national urban information system, Indian forest fire response and assessment systems, water resource information systems, space-based information systems for decentralized planning, natural resource census can be done, flood mapping and monitoring, and then tell me the list. You identify your objective, friends, and you can do the wonders. So remember again that the entire exercise depends on what? The entire exercise of applying the remote sensing depends on your objective, your skill of studies, and watershed monitoring and development can be there. Potential fishery zone can be studied. And there are so many studies. I'll stop here. So for you, what is the task? Remember, as a scientist, as a researcher, as a student, first is you can think of your role in fundamental research. In what sense? For observation of targets and objects. Number two, study on reflective properties of objects. And if you are focusing on applied research, application of remote sensing data with other information sources, and even application of technology. And lastly, technology for storage and processing, because huge amount of data are coming. How to store them, how to process them. So you require the best quality image processing softwares. You require best quality GIS software. You require best quality information management systems. And therefore, it is very, very important that where do you fit yourself? Are you believing in fundamental research? Are you believing in applied research? Or are you going to develop technology which can develop storage and processing of data? I'll stop here. Thank you very much. Yes, questions?
Dr. Saab?
Yes, please.
आप अपना ना can you please open up your chat box?
Chat box. Let me see.
Because people would participants would I think put in their questions in the chat box.
Monica may read it for me and I'll answer them.
I think that will be more comfortable if you open up the chat box. It will be easy for you.
Okay.
Monica can also do it, but I think it will be easy for you.
But okay. Today the question begins from where? First question.
First question is Muruga Puthi R.
Yes.
This is the first question.
Read it. Let Monica read it, because for me it is difficult.
Whether it is possible to measure the velocity of water in the river using remote sensing applications?
Muruga, what is this? Muruga is possible, but it is going to be very, very cost effective. Because cost intensive, because you require the information of every second to measure the velocity. Okay? Or you have to work out on it that from satellite imagery 1 and satellite imagery 2, the time difference has to be calculated. And if the time difference is there, okay, and if some object is there visible to you, that object A was at place A and then object B has moved to place B, then it is possible, right? But then it is going to be very, very cost intensive exercise, and normally we do not use it for the purpose of measuring the velocity. Okay. What is the question? Is it possible to control the spread of corona in the world using remote sensing
Using remote
technology?
sensing technology.
This is not possible to control the spread of corona using remote sensing technology, but one can easily understand the spread of it. And if you know the spread of it by using the GIS system rather than remote sensing, the problem is that in the remote sensing, the disease or the virus is not visible to you. So you have to integrate the GIS, and the GIS is going to help you because GIS will be able to map the data on the cases, and therefore the application of GIS in knowing the spread of the disease in a particular area, and then we can define if the cases are increasing over the days, then we can mark them as containment zones. That is possible, but remote sensing as a tool cannot help you to identify the disease in the space because remote sensing is used basically for the visual features. But indirectly, let me tell you, in one of the studies of the China itself, scholars like you, they'll try to find out the pattern of patients visiting the hospital. So they found that the number of patients visiting the hospital on day one or in the normal circumstances used to be very, very low. Suddenly there is a rise in the number of patients visiting the hospital in a particular period when a particular disease was discussed. Automatically the researcher will be able to correlate it, associate it, that there is something going wrong in this particular space because throughout the year this particular peculiar pattern of movement of patient was not found near this hospital. Suddenly on some days there is a peak and the huge number of patients were found all along the roads and near the hospitals. That means you are now correlating that there is something wrong, and then with the help of ground truthing you can find out that yes, there is a spurt of a disease, and because of this spurt of disease, this particular frequency of people or the too much of crowd near the hospital has increased. That means intelligently, see, it all depends on your intelligence, how intelligently you look at the images. So there is a possibility. Yes. What is the question? Next question.
How remote sensing is used for ground water table determination. Also,
Ah,
what are the applications of RS in hydrology?
good. Now, see, let me tell you again that as far as the groundwater means underground water. Underground water. See, underground water is not visible to you. But remember that underground water is linked with many associated factors, such as the geology of the area, the lithology of the area, the geomorphology of the area, the vegetation of the area, the climate of the area. So if you put them and integrate them together, and then try to find out that this particular vegetation at this particular slope and this particular geology in this geomorphological area, there is a possibility of this vegetation only, and you can easily estimate and identify the underground water. Let me tell you, underground water in the remote sensing image is not visible. So what we do, we try to correlate by having the different layers of information. So we have one information of the vegetation, we have one information of the geology, we have third information of about the lithology, we have the fourth information of the climate, and then putting them together, the rainfall patterns. And then if you know that rainfall has an ability to percolate in the sandy area, of course if the rainfall is more, you will have the rainwater underground, obviously. So this is how we correlate the information. Again, remember it that remote sensing as the data gathering tool will not be helping you independently. You are supposed to be a good data synthesizer. You are supposed to correlate and associate the data. And if you can do it, you can do the wonderful study even for underground water. Yes. Next question.
In which way remote sensing has been able to identify areas having mining potential under earth crust along with GS study?
Again, let me tell you that from the remote sensing satellite images only, it is difficult to identify. But then again, what we do, again we correlate. Again we correlate with the soil, the kind of rock structure we have. So you can identify the rock, and then you have to find out that if this particular soil is there, if this particular rock is there, what kind of mineral possibilities are there, and then you can relate it and correlate it. Again, from the satellite images, let me tell you, images are only for the visual features, but from the visual features you have to correlate it, and if you can correlate it, you can easily identify. Yes.
So there are no more questions.
Okay.
Okay, thank you, Doctor. Thank you very much for your presentation. You may exit now, and we meet tomorrow morning at 11 o'clock. Thank you so much.
Bye-bye.
And participants, please do mark your attendance. Do not leave the session without marking your attendance. Link is in the chat box.